Okay, we are moving on today to talk about the magnetic force on moving electric charges. So here's the idea, just right off the bat. If you have a charged particle and you're moving it in a magnetic field, it can experience a force. And it does depend on the relative direction of the movement versus the direction of the magnetic field. In other words, the force is going to be greatest when the particle moves perpendicular to magnetic field lines. And in this class, we're really just going to focus on being either perpendicular or maybe parallel, in which case you wouldn't get any force due to the magnetic field. So in other words, when the when the charge is moving in the same direction as the magnetic field, you will not get any force. But if you're moving perpendicular, you'll get a maximum force. My point is, we won't really do anything in between in this class. If you get into AP, when you learn how to use cross products and take components, then we will definitely do harder problems. But they're hard enough just keeping track of directions when you're talking about the perpendicular nature. So, talking about magnetic forces on charged particles. The forces on these charged particles are different from the kinds of forces we've seen before. The forces on gravitation, the forces of gravitation when you have two masses, and the electrostatic repulsion or attraction. In each of these cases, the force is going to be in the direction of motion. So, if an object starts moving towards another object because there's gravitational attraction, then the force was just going to increase, and the force is in the same direction as motion. But when you're talking about force due to a magnetic force on a moving charged particle, two things have to be true. First of all, the charge has to be moving. If a charge is stationary in a magnetic field, there will be no force on it. It has to be moving. And secondly, the force is going to act perpendicular to both the direction of the magnetic field and direction of motion or velocity of the moving object. So there's this mutual three-dimensional perpendicularity that's happening that can get kind of confusing until we use what we call the right-hand rule. This is a different right-hand rule than the curly-hand rule, the golf club rule that we use to find direction of magnetic fields in your current-carrying wires. So different right-hand rule. So here it is. Here's the right-hand rule. This is the way I teach it. Mr. Shortenhouse teaches it a slightly different way, and I think it might be different in your book as well. But I find this way to be most understandable. So here's the idea. If you think of the lines of magnetic field, so in this case you have the x, y, and z axes, and the B magnetic field line vector lines are moving in the z direction, positive z direction in this case. And so what you do is you take your fingers, and you think your fingers have multiple lines in them, right? You got 1, 2, 3, 4 fingers. You take your fingers and you point your fingers in the direction of all the magnetic field lines, and then you take your right thumb, again this is a right-hand rule, and we are assuming when you're talking about a moving positive charge, you use your right hand. If you're going to use a negative charge, like an electron, then you're going to use your left hand to try to understand forces. Okay, so we're talking about a positive charge. We use our right hand, our fingers point in the direction of the magnetic field, our thumb points in the direction of the moving charge. So as the charge is moving in this direction, that's the direction our thumb is, and our palm, the direction of our palm, is going to tell us the direction that the charge is going to feel a force. So you think about slapping something, you think about pushing something. It's that direction of the palm moving towards another hand when you slap hands. That's the direction that the charge is going to feel a force. So in this case, we have a little charge over here, positive charge, it's moving to the right, it's going to feel a force perpendicular. So, to use it in a diagram, when we talk about magnetic fields, we mentioned in class a little bit yesterday that we think about an arrow. And we think about an arrow as having a pointy tip, and then the back of an arrow looks like it has a little crosshair. So, when we think about the way an arrow looks, that's the way we would describe what is going on with a magnetic field. So in other words, in this diagram on the right here, where we have these little X's that are going uniformly spaced, generally, what that would represent is a magnetic field that is going into the paper or into the board. So perpendicular straight into the paper. And what you're doing by looking at the x's, you're looking at the tail end of the arrow. So that's to indicate the magnetic field in this case is going into the paper. And it's generally pretty uniformly spaced. And then you're going to take these little plus charges and you start moving them in a certain direction. Okay, and so then you have to think about, all right, what direction is the force? If you have a charge moving to the right, then what direction is the force? And so you take out your right hand and you point your fingers into the page or into the board, into the computer, whatever, with in the direction of the magnetic field. So your fingers go in the direction, and you extend your thumb, your right thumb, in the direction of the moving charge, velocity v, and then you feel the force on the charge is going to be in the up direction. So that's how you figure out that the force is in the up direction. In this particular case, if you get a charge moving in a uniform magnetic field, it's going to be here feeling a constant centripetal force. So wherever it is, it's just going to keep feeling a force in the middle. So that thing is going to get started because it keeps spinning around in a circle in the middle, rotating around, I should say, rotating around in a circle. It's not going to pick up speed, it's just going to be constantly changing direction. Okay, so here's some more examples. Use your right hand rule to think about the direction of the force. Okay, so the one on the left, you get your right hand, point your fingers in the direction, point your thumb in the direction of the moving charge, and you should realize that the force is going to be coming straight out at you. So I'm putting a little dot, meaning that the force is coming out at you. Okay, one on the right. In this case, you have little crosshairs, so that means the magnetic field is going into the page. You put your thumb in the direction of the moving charge, the velocity, and the force is going to be up. When we have evenly spaced dots or evenly spaced x's, that usually means that we're talking about a uniform magnetic field. So go ahead and try this one. If you have a positive charge and it's moving to the right, then the direction of the force will be in what direction? Okay, hopefully you figured out that it is in this direction with your right hand rule. And there it is. Okay. So if you have a charge moving in a uniform field, the force is always going to be directed radially or toward the center. So a magnetic force cannot speed up the charge, it can only change its direction. Well, how big is the force? If it turns out that the magnetic field is exactly perpendicular to the direction of the moving charge, the velocity, okay, so if those two vectors are mutually perpendicular, b and v, then the magnitude of the force is q, and that's the charge. Okay, these are all SI units, so the force in newtons is going to be q, the charge, that'd be in coulombs, v, the velocity, in meters per second, and b, the magnitude of the magnetic field, in Tesla. So for more general cases, if you don't have them exactly perpendicular, then the force is going to be q, v, b sine theta, where sine theta is the angle between the velocity and the magnetic field vectors. So the idea there is you want the component of the velocity vector that's perpendicular to the magnetic field. That's what the sine theta gives you. Cosine theta is going to give you the component of the velocity that's in the same direction, which you wanted. When did you want that? I think when we did work, right? But for this case, we want the component of a velocity vector that's perpendicular to the magnetic field, so we need sine theta. So the general form of F equals QVB, which works for mutually perpendicular, where the B field is this way and the velocity is this way, that's what you can use QVB. If you don't have that scenario where, let's say you have the B field going this way, this is B, and then you have the velocity vector going this way, what you're essentially doing is finding the component that is perpendicular. So that's where the sine theta is going to come into play. So here's theta right here. Okay? So QVB sine theta. Incidentally, for you calculus people, then you say is QF equals, the vector equals QV cross B. Okay, so the cross product. All right. Note, if the velocity is parallel to B, if the velocity is in exactly the same direction, so let's say the velocity is going this way, then sine theta becomes 0 and there is no force. Okay, so you always have to have a velocity or moving charge with some component that is perpendicular to the magnetic field. If there's no component perpendicular, then there will be no force. Lots of applications, old-fashioned TV sets, not necessarily the kinds that we use now, but those were used electromagnetics to control the motion of electrons to get them moving and traveling and then changing direction, and they would hit the phosphor on the front of the screen and light it up, and then you get nice color television. There are charged particles from outer space that are deflected by Earth's magnetic field, which is a really good thing because that can reduce the intensity of some of the cosmic radiation that might be bombarding us. It gets kind of deflected and bent and pushed away, keeping us safe from these cosmic rays. The aurora borealis is a collision of energetic charged particles with atoms in the high altitude atmospheres at the poles. So you get these high energy charged particles that are coming from outer space. They come in and collide with the atoms of our atmosphere and give us those beautiful color spectral. Okay, concept question before we go further. This is based on yesterday essentially, but okay, a wire is carrying current toward the top of the paper. At a point to the right of the wire, the direction of the magnetic field is, okay, this is where you're going to use the little curly hand rule. So the direction of the magnetic field should be, if you think about it, into the paper. So you would draw little X's like this. And incidentally, they're going to get tighter and closer together as you get closer, and they're going to spread out as you get further away, because we talked yesterday about how the magnitude of the magnetic field is inversely related to the radius away. Okay, so the answer is to the right. Direction of the magnetic field, is going to be into the paper on this particular scenario. So there it is, D is correct. Okay, example problem. Find the magnitude and direction of the acceleration of a proton. Okay, acceleration. We want to find F equals ma. Of a proton. Here's the mass. Okay, proton, positive charge. Moving to the left. Okay, at 10 to the 4th meters per second in a 0.3 Tesla magnetic field, which points into the page. Okay, so let's draw a quick little schematic of what's going on. We have a 0.3 Tesla magnetic field going into the page, so we'd say, all right, we've got a uniform field, looks like this. The magnitude is 0.3 Tesla. Then we're going to have a positive charge, a proton, and it's going to be moving to the left. So here's my positive charge, and it's moving to the left. So the first question is, what is the direction of the force? Okay, so find the magnitude and direction of the acceleration. Well, let's first find the force. So I use our right hand flat hand rule, I call it the flat hand rule, and we put our fingers in the direction of the magnetic field, and our thumb points to the left, which means the magnetic force on this moving charge is going to pull it down. So that's the direction of our force. So we got the direction of the acceleration. The acceleration in this case is going to be down. Now we need to find the magnitude, right? F equals Q V B. And so F equals Q, our proton has a charge of 1.6 times 10 to the negative, wow, that was weird. Okay, I'll pause for a second and answer the phone. Okay, 1.6 times 10 to the negative 19th Coulomb times the velocity, moving to the left at 2.0 times 10 to the 4th meters per second times the magnetic field, 0.3 Tesla, running out of space. So then the total force would be, I don't know, I don't have my calculator, but what I really want is the acceleration, which is all of that divided by the mass, which is 1.7 times 10 to the minus 27th kilograms. So that's how you're going to set it up. That's going to get you your acceleration. Is the force divided by the mass, multiply that out with your calculator, and hopefully you get 5.6 times 10 to the 11th meters per second squared in the down direction. So that is going to be your acceleration, which is really high acceleration if you think about it. When you get a really high acceleration like that, you can imagine you can quickly get a moving charge to change its direction very quickly. Okay, concept question number 4. Moving electric charges are surrounded by electric fields, magnetic fields, both magnetic and electric fields, and nothing. Now, we haven't really talked about this, but think a little bit about it, okay? If you have a moving electric charge, it's going to be surrounded by, it's going to be surrounded by an electric field, because all moving charges, or any charge, has an electric field associated with it. So if you have a plus charge, it's going to have an electric field associated with it. What we might not have discussed, but you could now consider, is if you have a moving charge, like for example, along a current carrying wire, so you have your charge and it's moving along the wire, you're going to generate a magnetic field that goes around it. So you'd say moving electric charges are surrounded by both. They have both magnetic fields and electric fields. Answer is C. Magnetic domains in a magnet produce a weaker magnet when, okay, so this is from your reading assignment. Hopefully you figured this one out. A, magnet is heated. B, magnet is brought in contact with steel. Magnet is brought in contact with another strong magnet. Magnetic domains are all in alignment. Okay, so consider what the right answer would be. Hopefully you figured out that to get a weaker magnet, the answer is A. By heating a magnet, you cause a more haphazard alignment of the domains, therefore weakening the magnet. If you bring a magnet in contact with steel, that's really not going to do anything. It has to be a ferromagnetic material to change it. If you bring a magnet in contact with another strong magnet, that could actually strengthen the magnetic domains to produce a stronger magnet. And then magnetic domains are all in alignment. When that's the case, then you have a strong magnet. So the answer is A. And C, a magnetic force cannot act on an electron when it moves, A, perpendicular to the magnetic field lines, B, at an angle between 90 and 180 to the magnetic field lines, at an angle between 45 and 90, and parallel. Okay, the question again is, a magnetic force cannot act on an electron when it moves. And hopefully you see that the answer is D, parallel. When a charge is moving in the direction of a magnetic field, so if they're parallel, your QVB sine theta becomes 0, so there is no force. So in each of these cases, you're going to have in part A, you're going to have the greatest magnetic force, and then if you're between 90 and 180, or between 45 and 90, well, whatever component of the angle is going to tell you how much force you're going to get. So you could still get, but I guess 180 you wouldn't get a force, but anything between those two you should. An electron is moving to the left in a magnetic field that points out of the page. The magnetic force on the electron is pointing in what direction? Okay, so if you think about it, then you're going to have a magnetic force. The electron is moving to the left in a magnetic field that points out of the page. So you have your magnetic field, and it's coming this way out of the page, and you have an electron, which is different than what we've been talking about. We've been talking about positive charges. This is a negative charge. And it says that the electron is moving to the left. Okay, so if you're using an electron, you have to use your left hand. So your fingers point out of the page, and then your thumb points to the left because that's the direction that the electron is moving. The force is going to be down. So the answer is E. When a proton is moving up toward the top of a page, the magnetic force is to the left. Okay, so here we go. You got a plus charge. It's moving up to the top of the page. The magnetic force is to the left. Okay, this is sort of a weird thing. You have to figure out now what direction the magnetic field is going. So which direction will your fingers go? So figure out the force is going left and the motion, velocity, is going up. So your thumb should go in the direction of the velocity, and then your hand, your right hand, because it's a positive charge, should have that palm out to push it to the left, which means the magnetic field has got to be into the page. Okay, into the page. Question 9. A proton initially moves perpendicular to a uniform magnetic field. As it moves, its speed... Okay, so if you have a uniform field, proton, and it initially moves perpendicular, so it starts off perpendicular, as it moves, its speed will stay the same because it's just going to create a circle and just go around and around and around and around. So if it comes in perpendicular, it's going to keep going in a circle and it's not going to pick up at any speed. Acceleration of a proton moving perpendicular to a uniform magnetic field is, right, the acceleration, that's just F over m, right? In the same direction as the velocity, perpendicular to the velocity, none of these, and 0. Hopefully you see that the answer is C. If your velocity is this way, and let's say your magnetic field is into the paper. Wait, I said in, I mean out, because I just made dots. Dang it! Okay, we're back. Sorry. Magnetic field is coming out of the paper. Motion is to the right. Then the force is going to be perpendicular to that direction. So let's see. What did I say? The acceleration. The velocity is going this way. That's my thumb, my point, my fingers out of the paper. So the force is going to be down. But the point is that as long as you're perpendicular to the magnetic field, your force is going to be perpendicular to your velocity. And that concludes our lecture for today.